Okay, good morning. So yesterday we began discussing about classification and we saw how it is different from clustering. But in clustering, you have a bunch of data and you have a similarity measure or a distance measure. Using that, you are divided into groups in such a way that within a cluster, the distance is small and across cluster, the distance is large. This is the basic guideline. Whereas in classification, right from the beginning, you are given the data points and the corresponding labels. Right, and so given a bunch of data and the corresponding labels, if you are given a new data point, you need to find out what is the label. So here we said that there are two broad, approaches to classification. One is prototype based, and other is the discriminant based, or discriminant function based. Right. So we saw the simple example where if you have a prototype for each class, right, M1, M2, M3, and if you have a new data point, right, depending upon the nearest neighbor criteria, you find out which prototype is closest to it, and then give the class of the prototype to the unknown point. Okay, that is the approach. So this is like single prototype case. That is, you just have okay. So this is just one prototype for each class, but that is a bit artificial because in general you can have, if you have a lot of data, so multi-prototype case, you might have a lot of data, like for example x1, x2, x something, x n1. So n1 points belong to class 1. And you have, and so on and so forth, and finally you have xn. So for each class, for the ith class, if you have ni points, then you need to use, you're better off using all those points to construct your prototypes. But then how will you find out when is the correct class? Any ideas? We have lots of points for each class. Then you need to make use of all of them to find out your prototype. You are allowed to use multiple prototypes. Okay, so how will you do this? Any suggestions? Where is our Krishnaji or Krishna Singh? I forgot his name.
Yeah, hi sir.
Yeah. Generally, you have a suggestion, right?
Like I have suggestion, but I can
Go ahead.
suggest
Feel
some
free.
classification.
Sorry.
I can suggest some classification algorithm, decision tree, random forest, XGBoost.
We talk about clustering. When you have multiple points, if you only a single point, then we do it like this, like in the left case. Okay. Then if you have multiple points, what do you do? Okay. So forget about it. I'll just explain. Okay. There's an echo. Can you please mute yourself? So if you have n1 points for each class, then you perform k-means over those n1 points. Maybe you can get k1 prototypes. Okay, so you get k1 prototypes for each class. Okay, so then what will happen is, let us say these are the prototypes for class 1, and these are the prototypes for class 2. So these are all class 3, these are all class 1, these are all class 2. Okay, if you have prototypes like this. Now if I apply nearest, so I want to know what is the class of unknown data point. Okay, so if we again apply nearest neighbor criterion, then if I have a, let's say, data point here, and so that's my x. So the nearest point to that is maybe this one, and that point happens to be a class 1 prototype. So the class of x is 1, class 1. So you can do it like this. The point is, it's a very simple approach, easy to understand, easy to implement, because just based on some kind of a clustering. So you have reduced the classification problem to lots of clustering problems. Right? If you have some k classes, you have k different clustering runs that you have to do. So it's a pretty simple approach, but in actual performance, it doesn't work very well. It doesn't give great results. It's a well-known experience. So therefore, we'll talk about a different approach, a second approach, which is discriminant function based approach to classification. So here, like I was saying in the last class, you imagine there are, let's say it's a 3-class problem. Imagine there are functions defined, like this. Y is equal to, so x is my input vector in RL, and y2 is equal to some phi2x, y3 is equal to phi3x, right? So if for x to be in class 1, what that means is y1 should be greater than y2 and y3. Okay, that's how the function should be, right? So similarly, x is in class 2, y2 should be greater than y1 and y3. Okay, now you can guess class 3, y3 is greater than y1, y2. So you want to define functions like this. And in terms of the functions, now if you have an unknown point, so x is unknown, you need to find out what is the class. How do you do that? Any idea, any suggestions? How do you do this? If I have unknown point, how will you find out? If I have 3 functions like this?
Evaluate y1, y2, y3.
Yeah, very good. Max of yi. Okay, I for which yi is max. Right? That so x goes to ci. Okay, so yeah. So if you want to draw this more pictorially, right? I will define 3 regions, or maybe. Okay, so this is the region where y1 is greater than y2 and y3. This is my phi1 of x region. So here y2 is greater than y1 and y3. Here y3 is greater than other two. So let us say this condition divides the input space into 3 regions. So this is the class 1 region, class 2 region, and class 3 region. So in principle, it is nice. You can define functions like this. Okay, so this approach to classification is called discriminant function based. This is a lot more effective, especially if this function phi can be made, very complex, complicated nonlinear function. You can get very complicated borders between these regions. You can define very complicated regions out of the input space. So this approach can be very effective. And also, if you look at the prototype-based approach, we have seen even in case of clustering, prototype-based approaches are not very effective. They're not great at getting good clusters, right? Because only when we moved away from prototype-based clustering methods, we were able to cluster very complicated data sets. Because one main problem is it is not able to capture non-global, non-globular shaped clusters. You'll have the same problem here also. Because if your class regions have very complicated geometries, then to capture such complicated geometry, you need to have lots of prototypes. So that makes the engine also very heavy, right? So the same drawbacks that you faced in case of prototype-based clustering methods, you will again face in case of prototype-based classification, right? So whereas if you take this discriminant-based function-based approach, right, it is a lot more effective, and this so it works. So let us actually now then talk about what is this discriminant function. So let me, for that, let me take the example of a 2-class problem. So people study a 2-class problem because in classification you need to have the smallest problem you can consider is 2-class problem. In 1 class, it doesn't have any meaning. right? So if you have a two-class problem, then if you want to make the take the same approach, phi1 is equal to phi1 of x, right? Y2 is equal to phi2 of x. Then for x to be in class 1, it means y1 is greater than y2. If x is in class 2, y2 is greater than y1. Okay. So here what we will do is, so y1 is greater than y2 implies y1 minus y2 is greater than 0. So now consider the function y1 minus y2, which is equal to phi1 of x minus phi2 of x. So this function has to be greater than 0. Now let us define this. We also define this as a phi such that x comma theta 1, and this is phi of x comma theta 2. What's the difference here between phi 1 of x and phi x comma theta 1? In this case, phi 1 of x and phi 2 of x are very totally different functions. That's what we assumed initially. Now we are saying both are the same family of functions. The only difference is in the parameter values. For the first one, phi 1 of x, it is phi of x comma theta 1 set of parameters. For second one, phi of x and theta 2, different set of parameters. So I'm taking the same family of functions. I'm assuming such families exist. I mean, imagine that there's a very general large class of functions which can take on any shape, right? And then just by setting the parameters, you can make it look like any function. Let's assume that such functions exist, and we have also dealt with such generalized functions. For example, Taylor series is one such function, right? Just by changing the coefficients, you can make it look like anything, or Fourier series, and so on and so forth. Okay, so such generalized function forms do exist. So let us assume that there is such a function form like phi of x. Now, if I take difference between two outputs, I have y1 minus y2, and that should be positive. So now let us define a function g, which is parameterized by theta, and that is equal to phi of x theta 1 minus phi of x. Okay, so this difference, because the classification depends critically on this difference, right? So now not on actual individual function, but only on the difference. So let me define a new function g, which represents the difference. And now the classification becomes like this. So sorry, x is in C1 means g is positive. Okay, x is in C2 means g is negative. So g becomes all important. So g is now called a discriminant function. So g is the one that is right differentiating the two classes. So we call it the discriminant function, and particularly g of x theta equal to 0, right? Determine what's the meaning of this equation. G of x theta is equal to 0. So we have a two-class problem. Okay, so I'll have y1 greater than y2 here, y2 greater than y1 here, right? Or in other words, g is greater than 0 here, g is less than 0 here. Now I'm saying g is equal to 0. What's the meaning of this equation geometrically?
That point belongs equally to both classes.
Yes, in this picture, what is that point? Or
Like on that line.
yeah, this border. This border is defined by this equation, here g equal to 0, or rather g of x theta equal to 0. So this is a, like, in two dimension, this is the equation of a curve, right? Because if x is two dimensional, some g of x equal to 0 will be a curve, and that curve acts like a border between the two classes. Right? We can loosely call it border, but more formally it is called a decision surface. Because Why is it decision surface? Because this is where you make the decision whether the point belongs to class 1 or class 2. Okay, so 0 is a critical point, region at the border. If you slightly change to one side, you get class 1, otherwise you get class 2. So this is where the decision is made, so you call the decision surface. Now, why is it called surface? We've been talking about it as a border and a curve and all. Because if x is 2D, right, the decision surface becomes a border, like a curve. But if in general, if x is n-dimensional, right, what is the dimensionality of this equation, the solution of this equation? So, sorry, if the input space is two-dimensional, let me go to the next slide. So this is y1 minus y1 is greater than y2. This is y2 is greater than y1. So this is 2D space. So the sorry, x is in R2. Border is one dimension. It's a curve, what we call a curve. That if x is in Rn, then the decision surface let us take 3D space. Difficult to draw this, but let us say I have like a surface. So on this side of the surface, y1 is greater than y2. This side of the surface, y2 is greater than y1. So here x is right. So and this is my g of x equal to 0. So now what is it? This is not a border, right? What do you call this? I mean, assume it's extending to infinity, some very complicated surface, right? So this is a surface, right? This is not a border. What's the dimensionality of this? Since it's a surface, how many dimensions does it have?
2 dimensions.
Yeah. So this is 2D. So if the input space is 3D, the decision surface is 2D. If input space is 2D, the decision surface is 1D. So in general, if the input space is ND, the decision surface will be an n-1 dimensional. Surface is a loose term. The correct mathematical term is something called a manifold. Manifold, okay? So that is what your decision surface is. So now what we'll do is, let us start with a very simple model. So now we need to take something concrete, right? Take a concrete function, phi of x, and then see how this decision surface looks like, what are its properties, and for a given classification problem, how do you find that decision surface? How do you find those functions? These are the kinds of things we need to now study, right? For that, we'll look at, we want to now choose a discriminant function. Let us choose a linear discriminant function. That means my g of x will be defined as w transpose x plus w naught. So this is a linear function. This is the simplest thing you can think of. If you want it to be linear, if you want it to be nonlinear, then you can have quadratic terms and cubic terms. It gets very messy. Linear, its life is simple. This same thing can be written as sigma wi xi. Right, I goes from 1 to small n is a dimension of x plus w naught. So they're all the linear terms plus a constant term. So now again, since this is a discriminant function, it defines a border. So if g of x is greater than 0, x is in C1, else x is in C2. So this is how you can solve a two-class problem, right, by using a linear discriminant function. Okay, and the same thing if you want so if you in 2D, what does this look like? Let me draw here an example. So n is 2, right? G of x will be w1 x1 plus w2 x2 plus w naught. Similarly, if n is equal to 3, g of x will be w1 x1 plus w2 x2 plus w3 x3 plus w naught. Okay. Now let us so in general it is a hyperplane, this kind of a function expression. So if you take g of x equal to 0, right, this is my Decision surface. So in case of 2D, if g of x equal to 0, what kind of a geometric object is it? In case of 2D, g of x equal to 0 is what kind of object?
1D order.
It's a straight line. It's a line, right?
Yes, sir.
Right, and in this case, w1 x1 w2 x2 w3 x3 plus w naught is equal to 0, or g of x equal to 0. What is this? What kind of geometric object does it represent, this equation? Let me go back. Okay, so let's take 2D. W1, so g of x defines w1 x1 plus w2 x2 plus w naught, okay, is equal to 0. What does it represent, this equation? Hello?
A straight line, sir.
Yeah. So similarly in 3D, g of x is defined as w1 x1 plus w2 x2 plus w3 x3 plus w naught is equal to 0. This is the Decision surface. What does this represent?
A plane.
Plane. So in ND, g of x equal to 0, I mean you can expand it, right? Equal to sigma wi xi plus w naught. This is called a hyperplane. Okay, of dimension n minus 1 dimension. Right. So these are some basic ideas we need to become familiar with before we talk about how to construct this kind of a Decision surface, which is a hyperplane. If G is a linear expression, the Decision surface will be hyperplane. If G is nonlinear, then it's called a hypersurface, an n-1 dimensional manifold. Okay, so let us work out some properties of this. Right now, I will draw 2D pictures, but the math itself is applicable for the general n-dimensional case. Okay, let us say I have, this is my input space, I'll call this x1 and x2. And this expression will be W transpose X plus, right? So the same expression, sigma W Xi and all that, I can write it as W transpose X plus W naught, right? So the Decision surface is W transpose X plus W naught equal to 0. And one more thing you might have noticed here is, so this expression is equal to 0 on a line or a plane or whatever. And since it's a linear expression, then once you come to one side of that plane or surface, it will be positive, and if you go to other side, it will be negative. So you will never again visit 0. So if you have in this case, this is a straight line, the 2D space, this is straight line, and on the line it is 0, the expression is 0. One side of the line, if G is positive, other side of the line G is negative. You will never see any occurrence anywhere where G is again 0. This is a property of a linear expression. I hope we're okay with this. We'll also prove this in a minute. But it becomes 0 only on this line. Everywhere else, it is non-zero. Not only that, on one side of this line, it's all positive, and other side of the line, it's all negative. And another thing, it keeps monotonically increasing on one side. The expression value g of x is 0 on this line, but on one side keeps on increasing, other side keeps on decreasing. So let us show these properties in a second. So first, let us show, right, the geometric interpretation of W. So W is a vector. Right, what is the meaning of this vector? In this, so g of x equal to 0 is the rotational surface, which is parameterized by this W and W naught, of course. What is the meaning of this? So for that, let us take two random points on the rotational surface. I'll call them x1 and x2. So on the rotational surface, right, we know that g of x equal to 0, which is equal to W transpose x plus W naught. Okay, so this we know. Since so let me call this ds. Since x1 and x2 are on the ds, right, belong to ds, g of x1 is equal to 0 and g of x2 also is equal to 0. So that is equal to W transpose x1 plus W naught. Okay, that's equal to W transpose x2 plus W naught. So now if you take the difference of these two, do 1 minus 2, then you get W transpose of x1 minus x2 is also equal to 0. What's the geometric meaning of this equation? Anybody? Or you can say W transpose, because x1 minus x2 is a vector, W is a vector, W transpose x1 minus x2 is 0. What's the meaning of this? Or I can say the same thing as W dot, like, because x transpose y is dot product, right? So W dot x1 minus x2 is 0. What's the meaning of this?
W and x minus x2 are perpendicular.
Perfect, yeah. W and x1 minus x2 are perpendicular. And x1 and x2 are any random points on this plane or this rotation surface, this hyperplane, right? So that means the hyperplane itself is perpendicular to W. So W vector, by definition, is perpendicular to this plane. So that's the first property of this rotation surface. So if you define rotation surface by Gx equal to 0, where Gx is defined as W transpose x plus W naught, then the W vector will be perpendicular to the rotation surface. So W is perpendicular to rotation surface. So this is the first property. There's another interesting property, like I was saying, if you, oops, oh no, oh shit. Is there any way to recover this?
What?
I kind of forgot saving all the notation.
Oh, okay.
Anyway, forget it. Mistake. Yeah, so let us take right. So this is my input space. I call this x1, x2, and this is my rotation surface. That is g of x equal to 0. So we know that if x is in the decision surface, g of x is equal to 0. But what if x is not in decision surface? What happens to g of x? This is what we like to answer. Okay. So if x is on the decision surface, g of x is equal to 0. If x is some point like outside here, because this is x, and I just plug this expression, this vector into g of x. So obviously I'll get some value. It will be not 0. But what's the meaning of this? Okay, so for that, what we'll do is we'll add some notation. So you drop a perpendicular from x onto the decision surface, right? And I'll call that point xp. Now this length of this line, right, this perpendicular, its magnitude, I'll call this r. Okay. Now if you plug x into this expression, so g of x is equal to w transpose x plus w naught. Now I can write x as xp. This is a vector xp. This vector plus this vector, right, gives me x. And what is this vector? What I'm showing here, the length of it is r, right? So x can be written as xp plus another vector of length r. And what's the direction of this vector? Anybody?
Along W's.
Yeah, perfect. So that will be w by mod w. Right, so because this is a unit vector in w direction. Okay, so I can express x like this. And I want to now plug this into g of x and see what happens. So g of x is equal to w transpose xp plus r w by mod w plus w naught. Now I can regroup terms and write it as plus w transpose xp plus w naught. What can you say about this expression? This is nothing but g of xp. What is g of xp?
0.
Yeah, why? Because xp belongs to the decision surface. Right, so therefore g of xp is equal to 0. So this whole thing becomes 0. This is r times w by mod w. Okay, so r becomes equal to sorry, no, I think yeah, so w transpose r times w transpose w by mod w. Okay, plus this whole thing. Now w transpose w will be right norm w squared. So that will be equal to r times w. Okay, so therefore r is equal to g of x by mod w. And if we even make a simplifying assumption, we can always let mod w equal to 1 if you assume that. Why is that? Because if I just want a decision surface, it is w transpose x plus w naught is equal to 0. I can always divide the entire equation by some lambda, both sides, just rescale all the weights in such a way that mod w is equal to 1, right? That option I always have. So if you do that, right, then r is equal to g of x. So what are we saying here? This distance of the point of a given point, there's a point which is not on the decision surface, right? This hyperplane. So it is away from it, and the distance is given by g of x. Just plug that point into the expression of the discriminant function. You'll get some number. That number tells you how far the point is from the plane, and that is definitely valid when the point is on the plane. When the point is on the plane, g of x is equal to 0, which makes sense because point is a 0 distance from the plane, right? But when the point is off the plane, g of x is non-zero, and its magnitude tells you how far you are, how far the point is from the plane. And not only that, if it is 0 here, and if it is positive on one side, it will be negative on the other side. And the r value tells you not only how far it is, but how far it is on which direction. Is it on the positive direction or negative direction? So for this reason also, you see that r will never again return to 0, because because since r represents the distance of the point from the plane, once you get off the plane, you will never become 0 again. G of x will never become 0. Okay, so the function will keep on increasing monotonically as you move away from this plane in one direction, or it will keep on decreasing monotonically towards minus infinity as you keep moving away from the plane in the other direction. So this is how the g of x looks like, right? What is the time? Okay. So yeah, one more small special property is, so if x is off the plane, we have seen what is the distance. If x is the origin, sorry, then what happens? If x is origin, then r is equal to again g of x in general by mod w. What is g of x when x is origin? Anybody?
W naught.
Yeah, w naught. So if I take a hypersurface of defined by g of x is equal to transpose x plus w naught, the distance of this hyperplane from the origin is equal to w naught by mod w. So that's another property. Okay, so all this is fine. Now, next thing that we need to find out is, given a classification problem, right? So let's say I want to solve a two-class problem, right? What does it mean? I have data given x1, x2, etc., xn1. All this is class 1 data. Then x n1 plus 1 blah 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 xn. All this is class 2 data. This is the data I am given. If I want to solve this using this discriminant function approach, I need to find out a g, right? Right, such that to find for x in class 1, g of x is greater than 0. X in class 2, this is what we want, right? So we have some points. So these are class 1 points, these are class 2 points. What does that mean? I need to find some g of x equal to 0 in such a way that on one side, right, all the class 1 points fall on one side of this hypersurface. All the class 2 points fall on the other side of this hypersurface. So how do you find out? So for that, we'll make a small change in notation so that an algebra works out to be very convenient. So what we'll do, we'll define a new quantity for D such that D is equal to 1 when X is in class 1 and D equal to minus 1 when X is in class 2. So why are we doing this? So we know that if X is in class 1, G of X is greater than 0, X is in class 2, G of X is less than 0. So if I have this new quantities called D1 and equal to 1 and D minus 1, then I can write this as so consider D times G of X, right? What is this quantity, is it positive or negative? D times G of X when X is in class 1.
Positive.
Because D is positive and G is also positive. When X is in class 2, then
Again positive.
yeah,
Oh wait, yeah.
this is now D is negative, G of X is also negative, right? So if therefore if G of X is the right function, that if it is able to classify the data correctly, D into G of X is positive for all X. Okay, so that's a condition, right? You know this notation, right? This is for all. So we need to find a G such that D, when it is defined like this, right? D times G of X is greater than 0 for all X. So for that, we derive what is called a learning rule, right? For updating all the weights in such a way that for all the data points X, D times G of X will be positive. Okay, so let us do that in the next class. And from then on, so this is what is called linear discriminant function based approach for classification. So we'll derive a learning rule, and from there on we'll look at some difficulties with or limitations of this approach, and from then on we'll go on to nonlinear functions. Okay, so any questions? We'll stop here. Any questions?
Yes, sir. I have one question. Like,
Yeah.
is it similar to logistic regression?
What is logistic regression?
I think that's all. Sorry.
So in regression, basically you just model a function. Here, this is slightly different. Classification regression is slightly different. I'll talk about regression also later. Right. In
No,
fact, yeah.
I think in logistic regression we classify or classify classes based on a particular this regression line. Okay.
I don't know. Let me read. I have to look it up. Okay.
Okay. Thank you, sir.
But actually, we later on will formulate classification problem also as a regression problem. Right. In fact, we have already begun doing it when we define this new quantity D. Right. That's the starting point. We are basically we can define classification as a regression problem, and then use the same learning algorithm for both regression and classification. Okay, I'll describe that later. I'll show you talk about difference later between regression and classification. Okay.
Yeah. Okay, sure.
Any doubts? Okay, then see you in the next class. Friday.